what we've done with all these discounting methods is we've basically subtracted from some counts and then given to 0 count events or lower count events. But we've actually ignored some important information that we have access to. Here what we've done with our absolute discounting methods is, or with our additive smoothing methods, is we gave mass to offer and we gave the same mass to loan and we gave the same mass to dog. Okay? But we've actually ignored some useful information. Maybe we know that loan, even on its own, just occurs way less often than the word dog. Okay? And then when we're spreading out the mass, maybe we actually want to give a little bit less of the probability mass that we've taken to loan and more to dog and offer. When we're moving mass around, we're ignoring a very useful source of information, and that is that some of the things that we're moving mass to might actually occur way more than other things that we're moving mass to. And a more formal way of saying that is maybe we can use information from the smaller context, a lower order endogram, when we're trying to estimate the probability for the higher order engram. Okay, and here's a little example to just motivate that. Okay, so we're drinking beer in Scotland. Okay, and we have a corpus and we've collected some of the counts from that corpus. And I don't think you ever thought you'd count so much in your life as you're doing now, but yes, that's what we're doing. And counting is probabilities, so it's fine. Okay, so let's say this corpus contains the word Scottish beer was 20. Scottish beer can 16, Scottish beer awards 7, Scottish beer brands 3. Okay, and then there are these two trigrams that we've never seen before, Scottish beer drinkers and Scottish beer eaters. So these two trigrams we've never seen before. If we just did maximum likelihood, what would be the probability that I assign to the word to the word drinkers, given that the preceding two words were Scottish and beer? What's the probability? We're just doing maximum likelihood, given that this is our corpus. 0. Okay, cool. And Scottish beer eaters? 0 as well. Okay. Okay. Now 2 questions. Okay. The one is, do you think this is reasonable? And obviously the answer is we really want to avoid giving absolute 0 to any of the probabilities, because then we just mark a whole corpus containing Scottish beer eaters as 0. Okay, so we don't want to do that. But maybe the follow-up question is, do you think Scottish beer drinkers and Scottish beer eaters should have the same probability? Okay, so what both of you actually told me is that I can, by looking at some of this, I can see that the probability for this should be higher than the probability for this. But I don't actually need to look at the word Scottish in order to tell me that the probability for the first one should be higher than for the second one. All I have to do is I just have to look at this diagram. Beer eaters probably occurs almost 0 times in my data set. Okay? And beer drinkers probably occurs more than 0 times. Okay? And the idea behind these language model n-gram regularization approaches is to use the lower order information when I'm moving weights over to these unseen events. Okay? And that's basically the idea. So the first approach that we're going to use that uses lower order information in order to basically figure out the counts for the higher order case is called interpolation. Okay, interpolation is really, really simple. So what we want is, let's just get this. So we want the probability of drinkers given Scottish beer as the preceding words. What we're doing is we're going to use a mixture of models. Okay, so if we're looking at a trigram, what we're going to do is we're going to say, well, let's use a little bit of our unigram, okay, weighted by lambda 1. Let's use a little bit of the bigram, and let's use a little bit of the trigram, okay. And maybe this is 0, that's fine, but then these two actually has some values to it. Okay, and we're going to add them up, and we're going to add these lambda 1 for the unigram, lambda 2 for the bigram, lambda 3 for the trigram. And for this to be a valid probabilistic model, we need these lambdas from little k to big K to sum to 1. And if we had that, then that's a valid probability. Okay, we have to choose these lambdas. We'll get to that in a second. Okay, so let's just look at our little example here. So we've got Scottish beer drinkers. Okay, and to calculate that, we are using our unigram model, we're using our bigram model, and we're using our trigram model. Let's contrast that with the other example that we were looking at. So let's say we're trying to figure out what the probability of eaters is given Scottish beer. I hope my Scottish friends don't kill me for, you know, talking about how much they drink beer all the time, but whatever. Okay, so we've got a unigram probability. Okay, what's the word that should go in unigram land there? Eaters, that's right. Sorry, I'm just checking that you're not full on asleep. Okay, plus lambda 2 p of bigram. What should I write here? Eaters, thanks. Given beer, that's right. Okay, and then the last one is just the actual one. This is probably low in both of these cases, right? Scottish beer drinkers never occurred, so this is a 0 probability. Scottish beer eaters also never occurred, 0 probability. But now if you look at the lower order bigram model, beer eaters probably has a low probability as well, but beer drinkers probably has a slightly higher probability. And that means that in the end, you end up with this interpolated language model, which actually assigns a higher probability to this reasonable sequence, Scottish beer drinkers, instead of assigning a equally high probability to Scottish beer eaters. Okay, and you've done that by basically smoothing out from the lower order n-grams to the higher order ones. You can actually also use interpolation between, not just between things of different orders, but actually just between different language models. Okay, and let's just write that out. So let's say we're looking at a trigram case, and we want the probability of our current word given the preceding two words, t minus 2 and t minus 1. Then what you can do is, let's just say for some reason I have two different language model, a P1, okay? It's also a trigram model, but it's different from the other model that I have, a P2. This will make sense in a second. Both of these are trigram models, but what I'm doing is when I'm trying to estimate the probability for this specific trigram, I use a little bit lambda 1 of P1 and a lambda 2 of P2. Why the fudge would we do this? Like, can you think of an example where you would just generally interpolate between two language models? I think that's spot on, right? Let's say we're building some model that looks at medical cases in South Africa, right? And you maybe have one domain here, which is like medicine, and here we've got another domain, law, and we actually want to incorporate information from both of these sources. Then you can interpolate between these different domains. That's spot on. An example where we've actually used it is we were doing broadcast news speech recognition in South Africa, and we had a very big language model trained on broadcast news from the United States. Okay, and then what you can do is you can take your big model from the United States and interpolate that with your model from the domain that you're actually interested in, and use that in the local context. And maybe the counts from the big language model is way better than the one from the smaller language model, but you're still getting some access from the local domain. Another example, and I'm not sure they actually do this, but you know this thing when you swipe on your phone and it does predictive typing, telling you what words to follow. Now, if you use this Microsoft Swift keyboard that I use, the first few times I'm just typing, it actually doesn't know what, it guesses some words, but it doesn't really match the way that I type, okay? But after a while, it actually starts to predict the next word that matches some of the previous things that I've written, right? So what they could do is they could maybe train, Microsoft could train a big language model on all the previous people on Earth that use the keyboard, okay? And then what they can do is, as I'm using the keyboard, they can actually start to build up the counts for me using specific word combinations, okay? And then what they can do is when they're actually trying to predict the next word, given the 2 preceding words that I've typed, they maybe take into account the whole Earth, but they also take into account my local way of, and my specific way of writing, and you can actually interpolate in that way as well. Okay, make sense? Cool.